Hello, so today we're going to talk about Riemann integral and Riemann sum because I noticed that the definition or the concept appeared in the question list that was shared by the principal in class A section in the Google Classroom. So I'm not sure if section B already covered it, but I think it'll be great to illustrate it all over again because when we went through the questions in the question list in section A, we found out some of the Riemann sum or Riemann integral questions are not trivial. So I think nevertheless it'll be worthwhile to illustrate it, and also for the students who missed classes in section A, it'll be good to catch up because I don't think it's something that would be easy to learn on your own. So a higher level grasp that when we define like an integral, this is a new operation. It's similarly just like we define derivative. So we use like the simple operations that we know. So for example, for Riemann integral, we take the Riemann sum first. So higher level from operation perspective. So Riemann sum is basically just summing of functions. So in higher level view, but it's yeah. So for example, summing fi times delta x, and then delta x is some interval on the x-axis, and of course, and the sum could be I from 1 to n, could be like many functions, but Riemann sum is nothing, is not that fancy, just summation operations, right? Summing the functions times like the length of an interval and then summing up together. So summing up is some basic operation that we know, but to make it like a more powerful operation, we simply take the limit. So first higher level overview, Riemann sum, we take the limit, and then we can invent a new tool, a very powerful operation as called we'll say is Riemann integral here. Yeah. And then recall we actually, it's actually not the first time that we've seen this kind of development, right? So recall. So recall just think about if you are like an old mathematician in ancient times, how does the math theory evolve over time? You first create something like a more basic summation operation that you know, and then it's like upgrade this operation. So we did something similar. Recall the definition of derivative. So remember, the definition of derivative or the first principle also involves something like taking the limit, right? So yeah, so it's the same thing that if we have like the average rate of change would be like the difference value of function value f and the delta x, right? Delta x is the difference of the x values, and so this like delta f and delta s, they are just difference, right? The minus, so it's like it's like taking summation, but like taking a negative summation, right? So delta f is fa plus h minus fa, and delta x here is just delta x here is usually a plus h minus a, so delta x is h here, right? And so these are operations that we know, and like this quotient means like the average rate of change, but when we take the limit, this becomes a more powerful operation. So limit, let delta x take delta x to 0, so it's like the instantaneous rate of change, right? And when we evaluate that s, it becomes limit h goes to 0, right? So, and then we define the limit as h goes to 0, delta x goes to 0, this fraction. This is our powerful tool, is the derivative at point A, right? And also the last time, or for section A class, last time we talked about the position function as t, right? And what about s prime t? So first we take the average rate of change of the position function, and we talk about the position. We can also view it as a length, right? Or the height. So it can be height as well, right? So just a change of location, right? So first we have the average rate of change is delta s over delta t. So these are basic operations that we know, but when we take the limit, and then this become our derivative, right? And similarly, so and then this means like the velocity at time t, and similarly we have the height delta h delta t. Okay, yeah. So integral is like the other way around. So we still have like a basic operation, but instead of taking the fraction of dividing something, we multiply something. All right. So just think it through. So taking derivative is like average change, but so we divide something, divide delta s, so divide delta t, and then take the limit. Let the the independent variable, like the change delta x or delta t goes to 0, and we have derivative. But the integral is the other way around, is multiplying the like the subinterval, and then we summing them up, and then later when we construct it, we take the limit, it'll be Riemann integral. So first we are going to proceed through the Riemann sum of one variable, okay? Riemann sum of function of one variable, okay? Yeah, so what we just talked about is a higher level overview, so that you later, after you learn a lot of things, a lot of definitions, but you don't get lost from the bigger picture, right? So we always, I guess we start from something easier. Assume Let's assume y is equal to fx greater or equal to 0. And when we have a function, here is good to specify the domain. So the interval of x that we're interested in, like we just say a, b. And so for higher level overview, the Riemann sum or Riemann integral is actually the area that's underneath a function. All right, but Riemann sum is the area of rectangles underneath the function. Okay, so just a like a story that your first impression of Riemann sum. So the area of rectangle underneath a function. Okay. All right. So so what does the area of rectangle mean? So usually when the ultimate goal, like the Riemann, say the Riemann integral, would be the area underneath the function, right? But however, in older times, people discovered that but it could be hard to calculate the area of a function of a curve when the curve is smooth. So it'll be just like if you heard of the story, is in old times. Well, it's still like geometrically how to calculate the area of a circle when the the outer parameters of the circle is smooth, right? So it's hard to, you know, decompose it into pieces and summing them up. So it took a long time to actually investigate how to calculate the area of a circle, right? So because the circle, the outer parameter, this line is a smooth curve, and also for arbitrary function f, and here we only talk about the positive function. If it is a smooth curve that we draw on the 2D graph and is hard to calculate the area underneath this smooth curve, right? So the first step in Asian people think about is to use the Riemann sum, which is the area of rectangle, summation of the rectangle underneath the curve. All right. So, but then how do we calculate? How do we sum up the rectangle? So this is a process that's very important to calculate the Riemann integral. Okay, so what I'm going to say is very important. Um, this process. So so right now I'm not just telling story, right? Uh, telling story, but it's actually the thought process whenever you want to calculate the Riemann sum. Okay. All right. So step one. So these are not just storytelling, but you should take it as part of a definition. How do we define when you have a function and define Riemann integral? Okay, so first thing is divide or partition domain. So x is in AB, right? So we will have a assumption like AB interval is our domain. Into we define divide. Divide just means you have, so for example, this interval is a piece of paper that you have, like a piece of paper you have in Christmas and you want to decorate it. You cut it into equal sizes of smaller pieces, smaller intervals. Okay, so divide partition domain into usually in general is like n equal subintervals. Yeah, so just think of when you do Christmas decoration, you cut a piece of paper, like a, I don't know, a wrap, like a wrap decorating like a paper. You cut it into equal sizes, and here we can maybe pick six here. Okay, six here. So one, two. So these are two intervals. Okay, so we keep going, and 3, 4, 5, 6. Okay, so I'll just change it a little bit to make it look like equal sizes. All right. So then, what is each subing? So 1, 2, 3, 4, 5, 6. So then, what is each of these smaller pieces? And we call each of these smaller pieces, we call them delta x. Okay. And then it's important here we define the subinterval delta x. Okay, delta x is, what is delta x? I think you can calculate it, right? Because the whole length is b minus a, and then we're just gonna divide how many pieces here, because I'm not able to draw n pieces when n is very large, because I'm a human. I can only draw finite many. So we take an example. So for example, 6, right? So here is just b minus a divided by 6, right? Because in total there are 6 smaller pieces of them, of delta x, and then I can also call this is delta x. All right. Yeah, so the length of delta x is, here is b minus a divided by 6. And what about the general formula? I guess you already know, because 6 is only an example that I give of the parameter n, right? So in general, the delta x formula would be b minus a divided by n. Okay, so this is our step interval. All right, so I'll draw another graph here just so that you don't forget in the future. But I think it's pretty straightforward, isn't it? So you have x-axis, we have a general interval. So if you have an interval, and then the problem, you should see what's its requirement of this n parameter. Okay, so how many equal sub intervals that it requires to get, right? So our left endpoint would be a, and then after partitioning it into n intervals, and here is 6 intervals, and the first interval will be like this point, left point is a, right point is a plus delta x, right? And then okay, and then here this point is a plus 2 delta x, right? And then each of this interval is delta x and delta x and dot dot, and each of these are delta x, isn't it? Okay, right. All right. So and then to calculate the area, I guess we still have a lot of work to do, right? Because as you can see, like we have something like a base, like this length, right? And then we still have something height, because this function have a height. If we want to calculate this whole area, there's a like more thing to do. So the main idea of Riemann sum is that we decompose of this graph into rectangles. So as you can see, we already have the base, and then so for example, if I pick the left point of the first interval, the first delta x here, pick the left endpoint, and I take how tall is this function value fa, and then I can draw the first rectangle, and it look like this. Okay, the first rectangle, the base length, which is this delta x, the side of the at the bottom, right? And then the height is here, is fa, right? This height is exactly the function value f at point A, right? And then the rectangle area, how to calculate the area of a rectangle is just multiply the length, right? So if we have rectangle, this is the L1 is the first side, and then delta x is the second side, and then the area is just L1 times delta x, right? So the area of the first rectangle will be FA times delta x, okay? And then we proceed to the second interval delta x, and then we still decompose it using a rectangle, but right now, I guess here the graph, I can draw it even like more dramatically. I can draw it here, okay, so that you can, so that it's easier to illustrate, right? But the idea is the same. Okay, so let's say this is the first rectangle, and then proceed to the second rectangle. It's a matter of how we gonna pick the height of the second rectangle. So we actually, there's sometimes we can pick the middle point of the second interval, and then using this middle point to evaluate its function value here, and then pick its height. Or we can pick the or in other way, we can pick the left point. So I'm gonna illustrate it. So So there are different ways to pick the height of the rectangle. So, but here at the first example, the first graph I'm gonna illustrate is that we take the height of our take height using left endpoints of small intervals. Okay, so when you take a problem of Riemann integral or Riemann sum, in the problem it'll actually ask you to specifically use the left point or the right point of interval to calculate the Riemann sum. Okay, so the first example I'm going to give is take a height using the left endpoints. Okay, so the left endpoints of the second, when we proceed to second subinterval, will be this one. All right. So if this is our height, if I take the height here and then I just draw a horizontal line here, and as far as like the second interval here, right? And then this is the area of the second rectangle. Yeah, but for different requirements, for example, you can also take the right point as your height, and then as you can see, if I for the second subinterval delta x, if I take the right endpoints and then taking this f, it'll be so this is fa plus delta x, and then this f is fa plus 2 delta x, and then take this height, and we will see the rectangle will be taller, right? So the area will be like more, and then you can see this area, this rectangle, if it's taller than the curve, and then the area that we calculate of the Riemann sum will be like over the area underneath the curve, right? So yeah, if you got confused, it's totally fine because we're gonna keep drawing. Okay, so far we finished the second one, and then we just keep iterate this process. So it's like an algorithm, right? It's like the algorithm. We just keep drawing these rectangles, and until we exhaust, until we use all of the subintervals of our domain A and B. Okay. Yeah, so I hope this story you're comfortable with until the last. So these are dot dot dot, and then until the last subinterval delta x, I still pick the left endpoints of my last interval. This point, right? And then I draw a rectangle, so a horizontal line, and then draw this, and then these are all my rectangles that I need to calculate. So, and then the step two, what is the step two? Just gonna deduce from our process. We deduce what is Riemann sum, okay, and then furthermore, what is a Riemann integral. So step two, so area of let's see, area of rectangles in domain AB to approximate. Yeah, so keep in mind the higher level story. Why do we even care about drawing these rectangles? Because usually this function curve is smooth. It's hard to calculate. In ancient time, it's hard to calculate the smooth area, like the area below the smooth curve. So we decompose it into rectangles, and we summing up the area of the rectangles, right? So the idea is not hard. So area of rectangles in domain AB to approximate. You see, the idea is to approximate areas underneath F. Needs F and above 0, okay? Because at the beginning of studying Riemann integral, we have this assumption that we only care about the curves above 0. Of course, we can also integrate like the function beneath 0, but it's just a matter of a little bit modification, right? So okay, so to approximate the area underneath f above 0, right? So we make it rigorous, and so now the Riemann sum is, so this is our Riemann sum, okay? The Riemann sum, take a high level overview, is just the summation of rectangles. So we take, so for example, FA times delta x, right? So, or because the first graph that we take is taking the left endpoints of each of interval. So it's like taking FA times delta x and then plus FA plus delta x and then times delta x and then dot dot dot, and then until we have the until the last rectangle, right? So before we're writing out the whole formula, I'm just gonna modify it a little bit. So I'm gonna say, so f instead of fa, I write it f I star, because each of these are some xi that's on this interval a b, right? And we partition and decompose it, so you can think of this as x1, x2, x3. So and also if we take a middle point as our height, it's gonna be some x, right? So I'm just gonna say a general formula. We use the notation of x star I times delta x, and then we summing it up. So I from 1 to n. So these are the 1 to n. These are the number of subintervals, like how many of these little delta x that we have to in order to construct these rectangles, right? So I from 1 to n is just the number of rectangles that we draw here. You can actually count here because the actual problem will give you what is n, like give you just a small number like 4 or 5. So don't be scared of it. So and then so this is actually just our Riemann sum. Riemann sum is just this, right? Summation of the area of rectangles. Okay, and then summation I is from 1 to n, and then inside of this big bracket is our area of each rectangle, right? Area of each rectangle. So I think some of you, when you read until now, you may still have question about this xi star. Don't worry. So we'll keep drawing another graph. Okay. So to illustrate this xi star. So, but before that, I'm just gonna again illustrate this. Make a remark. So this blue thing. So summation of n of this multiplication. So each of these small x fxi times delta x would be the area of each rectangle, okay? And what we do is just summing them up. All right, so we calculate the area of each rectangle and then we're summing them up. So the reason that I use fxi is that, so first graph that we draw is using the left endpoint, but however we can also use as we say the right endpoints. Okay, so here I'm just gonna draw it again. So the f can be any like shape, but I'm just gonna keep things simple. So that's the reason I draw in this way, and then we have the domain a, b, and then decompose it into, again, like 6 intervals, and each of these is delta x. And again, when we draw rectangles, so from here to here, we want to calculate the area, but we approximate by rectangles. And so here I use so calculate the height using right endpoints of delta x. All right, so and then instead of, so first delta x, so still the base of the rectangle will be the delta x at the bottom, but what about the height? Instead of, so for example, take an example, we start with the first rectangle to calculate. Instead of FA, I pick the right endpoint of a rectangle here, right? And then the height would be a little bit taller than the rectangle here, right? Because here is below, is definitely like shorter than the curve, right? But here, well, it also depends on how our shape of F is. Our shape of F, it can also be here, and then if we take the right endpoint, it'll be, the rectangle will be even like shorter than it will be still shorter than the curve. But in this case, if the function shape is like this, and then if we take the right endpoint, so for example of our first interval, and then our rectangle will look like this, right? So taking right endpoints will be different than taking the left points of the area that we calculate, right? And then proceed to the second interval, and then we still taking the right endpoint, and then evaluate it at on the curve F, and then we take this point, draw a horizontal line because we want to draw a rectangle, right? I think you're very smart. You probably already know the process. So, and then we repeat until the last one, until the last interval. And I take the right point, and so here would be like FB, right? Here are last interval, the right endpoint would be FB, right? So I again take a horizontal line and I draw a rectangle like this, right? So on the top one, this would be like the height, the last height that we take would be this is actually FB minus delta x, right? All right, here. Okay, so and as you can see, there's difference of the area of rectangle when we take the left endpoint and the right endpoints. And then you may have a question of, and then the Riemann sum, which is the area of rectangles, will be different. Yes, exactly. It will be different when how you choose the xi, how you choose the height. Okay, so Riemann sum evaluation will be different. Picking different fxi, so the height of the rectangle, right? Be different. Picking different xi star, okay, which is the height. So you pick it according to the function, like the problem requirement, right? The height of rectangle. All right. So Riemann sum could be different, but however, when we take the limit, that's the magic. That's a great point of limit, is that when we take the limit, no matter how you take the height of the rectangle, whether it is at the left point here or the right point or in the middle of the interval, it'll be, when you take the limit, it'll be the same. So how to take the limit? So Riemann integral, taking the limit, it just instead of taking n rectangles, we take we take n to be arbitrarily large, okay? So Riemann integral, so a b f x dx. So you should think of how, so this is like a new symbol that we know, right? We never talk about this symbol yet, but you should really think of, you see, when you compare these two formulas, you should really think of this dx as another way of thinking of delta x when delta x is very, very small, because when we take the limit n goes to infinity of all partitions, okay, of all partitions. So, and then the summation of I is equal to 1 to n f x I start multiply delta x, right? Like also the big bracket here, okay? Yeah, so when we take the limit, it's like taking all partitions, right? The story, but well, you don't need to write all partitions when you write a problem, but a rigorous definition, like when you go to college, when you go to university, is taking all partitions, but we take the n goes to infinity, so their limit. So no matter how you calculate the rectangles, when you take the limit n, it'll be approaching to at the actual area of this smooth curve. Okay, so the way that to think about this is, let me draw another graph. So I guess I can draw here. And then when you take n goes to infinity, so each of these small interval delta x will be just arbitrarily thin, right? So that like even our eyes couldn't visualize it. So this is an amazing invention. I hope you think it's interesting, because is really an evolutionary idea of taking the limit, right? So here, when we take finitely many, each delta x actually have a length that maybe we can calculate or we can visualize. But when we take infinity, it's like infinitely thin, uh, delta x, and then each of these rectangles, like the blue area, become infinitely thin lines, right? Vertical lines. And then as n goes to infinity, there are just like infinitely many of them, right? And then, so because these rectangles become arbitrarily thin, and then the difference of the rectangle area and the uh, the smooth curve area below the smooth curve will be arbitrarily close, right? So this rectangle will be arbitrarily close to the actual area underneath the smooth curve, right? So as n goes to infinity, so the rectangles approximate the areas be underneath the smooth curve, okay? All right, so you should think of in Riemann integral, it's nothing mysterious, but just taking the limit of Riemann sum, and the limit is when n goes to infinity and across all partitions, okay? And then we can also take a small example, like it's the same with the problem set of that unit 1 question list. I don't know if section B students have this, but I found but whatever, there's a comprehensive questions, they also proceed from like more fundamental, like easier question steps, right? So we can say like start from a easy example 1, and then we take our f as, we first define our f. Y is equal to fx equal to 4 minus x squared, and then I'm gonna make this question easy. So let's do like 0 to, like, at the beginning we just care about the area above 0. All right, so, and I guess we can talk about it more, but if I require using the left endpoint, so first is partition into 4 subintervals, and then take Riemann sum using left endpoints. Okay, so I think you can do it on yourself, but yeah, but I can briefly illustrate it to you. We can talk about the more complicated question later. So first step, partitioning into 4 intervals, right? So this is always the first step that you're gonna do, and then take the left endpoints. Yeah, so the first rectangle height will be the left endpoint here, right? And then the second rectangle will be here, taking the interval of this delta x of this left endpoint here, and then the height should be looking like this and this. All right. So then what is the Riemann sum? Actually, I wanna let you to do it before we do the next question, because this is actually easy, right? Just summation of the area of 4 rectangles. Okay, what is fxi star? I already tell you it's a left endpoint, right? So it's like f0 times delta x. And what is delta x? You can actually calculate delta x using the formula that we have, right? And then plus f.5 times delta x, right? It's the second interval. So we partition into 4 subintervals, so 0, 0.5, 1, 1.5, and etc., right? And then, so I guess I almost read it out, and dot dot dot. I'll leave you to do this and see if you can finish this. But this is just easy, right? You just multiply 2 numbers. You just need to calculate this and summing them up. This is Riemann sum, and it is that easy. And we stop here for now because I don't want you to get overwhelmed. Okay.